morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. Today we will start module 9, that is the distribution network resiliency analysis. So, in this topic or model we will start with the what is introduction to resiliency, that means what is meant by the resiliency, what is the scope of the resiliency and why we have to do the resiliency analysis for the distribution network. Second, we will focus on the fragility analysis of the distribution network circuit elements, whatever elements we have studied before, that elements what is their strength and how much they can stand tall in front of all the hazards and the resiliency concerns. Third, distribution network resilience against extreme weather events, and at last we will see the wildfire resiliency in the power networks. So, first we will see what is resiliency. That the term resiliency is started from a word called resilio, that is a Latin word and which is meaning by to bounce back. So, it was first introduced in 1973 by C.L. Hollings in the context of ecological systems, and now we are adopting it slowly for the power networks as well. So, according to Hollings' definition in 1973, resilience offers to the capability of a system to retain its operation after a disruption. So, what does it mean? That your system was first running smoothly, it is under normal operating condition, and suddenly you got some disturbance or disruption in the operation. So, after that as well, if your system can retain or can continue with its operation properly, then you can say that your system is a resilient system or your resiliency is very high. So, over the time the definition of resilience has evolved across disciplines. In 1995, it incorporated the idea of systems buffering capability to absorb disturbances in a timely manner. So, in 2003, the concept further matured to include self-healing capability, highlighting a system's ability to recover and adapt dynamically during ongoing disturbance. That means, not only just to stand tall, but if you also become weak after a disturbance, but you have the capability that it again cope up or you can recover that disturbance and come to the online or to the operation after a certain time of operation. The resilience now broadly refers to the system's ability to rebound from severe disruptions, whether physical, cyber or operational, while maintaining critical functionalities and ensuring rapid recovery. So, that is how you can say what is resiliency for a power network. So, why you need resiliency study for a distribution network? First thing is that your distribution networks are highly vulnerable. What does it mean? That it is exposed more to the nature. Nature means like your transmission system, they are very tall towers, right. So, reaching to that transmission towers by any tree or by any other means is very difficult, but distribution network poles are quite shorter in length or shorter in height. So, distribution networks are more exposed than the transmission system due to their widespread physical infrastructure and proximity to external hazards. First of all, your distribution networks are not that much, you can say, strong enough. Your transmission towers, you must have noticed, there is a very tall, a very rigid construction, but your distribution network poles are mainly made of steel or your woods. So, they are more exposed to the external hazards like storms, trees and flooding. As the height of the poles are very short, so it is very common that a branch of a tree can fall on the wires. Okay. So, and also it has a radial architecture. So, that means if it is like that and in this line a tree falls and it goes out of order because of the fault, then entire network after that will become dark. So, that is more vulnerable in the distribution network. Service to end user. These networks deliver power directly to the consumers, including critical facilities like hospitals, water treatment plants and emergency services, making their continuous operation vital. So, if your distribution network is experiencing any fault or any kind of a disruption, you cannot allow it for a very long time, because major critical appliances or major critical customers are connected with the distribution network. You cannot afford a hospital to be in dark or without power for 5 to 6 hours. Then all the emergency services or emergency machines will be shut down. Okay, so that will cause casualties. So service to the end user is a critical thing. So distribution network resiliency has to be a concern. Then increasing threats, that is the climate change, urban growth and aging infrastructure increase the frequency and impact of disruptive events in the distribution systems. Okay? Because distribution networks are not that much monitored, so whatever installed 20 years back, those are not monitored and maintained in a timely manner. So the poles, the lines and the infrastructure has become very weak. So if any little bit of disruption or hazards occurs, so after that what will happen? It will become brittle or it will break down very easily. So if a high wind goes or a little bit of, you can say, hurricanes or floods is coming, then what will happen? It is very easy that the distribution poles will pluck up and it will fall down. So that is very easy concern. Then you have decentralized resources. The growing integration of distributed energy resources like solar panels, storage and electric vehicles require updated strategies to enhance resiliency. So those are the DERs. You are connected with the network and you can use them for enhancing the resiliency study. Regulatory and economic policies, utilities ensure to improve reliability and reduce outage duration and frequency. So if you are causing any outage, you have the government provision for the distribution utilities that the outage cannot be more than a certain limit. You cannot keep your customer for dark in 24 hours or let us say 1 day, 2 day, 5 days, 7 days. You cannot, you have to restore the service as quick as possible. So these things you have to consider, and because of these constraints, the resiliency studies has becoming more popular or becoming a big concern for the distribution network operators. So what are the key features of a resilient distribution system? Distribution network resiliency refers to the ability of an electric power distribution system to withstand, adapt to and recover rapidly from a high impact, low probability events such as natural disasters, equipment failure or cyber attacks. So the recovery is not from a very ordinary situations. That means what is happening in a regular basis, okay, like load change or let us say a small fault occurred. It is not like that. It is an situation which occurs very rarely, but when it occurs, that will completely disturb your entire network. If that is happening, at that time your resiliency algorithm should operate properly, or if at that time your system can retain its operation, then you can say my system is a resilient system. And what are those this kind of disruption? You can have a natural disaster or suddenly let us say a substation failed or breaks down, or let us say a pole has fallen down. So if this kind of disruptions happen, these are very rare, but if this happens, then how you can cope up? So what are the features you should adopt to make your system more resilient? First is the robustness, that is the physical strength of the infrastructure. That will make your infrastructure very strong, that if any natural hazards will occur for a low level, it will not pluck up. That means it will operate, okay, it will be there, it will not fall down. So that means harden your lines, make a very strong lines that will not very brittle, or you have underground cabling. So avoid having overhead lines, put cables underground. So that will be lesser affected by your natural disasters or more less exposed to the faulty events. Second, redundancy, availability of alternate paths and resources. That means if you have a radial network and something happened to this network, you must have a alternative switching path that you can send power to the underneath network, okay, that you will close that switch and you have an alternate path if this goes out of order. So that means you have a redundancy or redundant connection for an alternative path or rerouting the power to the disruptive or disrupted customers, okay. Then you have resourcefulness, that is the ability to mobilize resources and reroute power. Okay? That means you have mobile, let us say battery storage, or you have electric vehicles, or you have any other means that will be easily sent to the customers who are experiencing these hazards, who are actually under the hazard condition. So, you can send the help to them directly, so that the resource cannot be scarce, or they are not experiencing any scarcity in the electric supply. Okay? Then rapidity, speed of response and restoration. That means if anything happens bad, the restoration service should be as quick as possible. That is, at the less interruption time, the duration of the interruption should be as minimum as possible, and within that time frame you will restore your supply to your customers. So, depending upon that, your resiliency can be of two types. First one is a short term operational resiliency, that mainly focuses on systems' ability to maintain electricity supply to consumers immediately before, during and after extreme events. That is, during the events, that suddenly a hazard happened, at that time disruption happened, but you have to still cater some portion of the load or some portion of the customers from any backup supply. Okay? And at that time you will also, at the during the extreme event as well, you are capable to scatter few portion of your load, not completely shut down your entire network. If that is possible, then operation resiliency is possible. Depends on operational policies, real time system response and remedial actions tailored to different load and generation characteristics. Okay? Evaluated using performance metrics that reflect system behavior under stress in the short term, that will evaluate that during that situation how much your system has been stressed. So, and what measures you have to take to relieve that stress. So, that is called your operational resiliency, or that is called online resiliency. When the hazard is happening, at that time you have to take the action. In contrast with that, you have long term infrastructure resiliency. That means you make your system hardened, or you make your system prepared against any hazardous events or any extreme events. That means not only operating, or that means not only at the duration of that hazard you will act to improve the resiliency, but you will prepare your system like that. Okay? So, refers to the physical strength and durability of the system component against extreme events over time. So, you make your system strong enough that if something happens, it will stand tall, it will not fall down. Okay? So, involves planning and designing strategies based on historical data and predictive modeling. That means, you will plan your system accordingly, that your poles, your lines will be that much strong, you will put that type of material that it will be withstand that hazard or extreme event very easily. So, aims to improve system robustness through infrastructure upgradation or expansion strategies. Okay? We will see these things in more detail in later lectures. So, resiliency improvement measures in power system, different levels of that. In the generation system, you can, at the operation resiliency, you can make sustainable fuel supply, keep the fuel supply continuous, reliable fuel storage, keep some storage is a backup fuels, that you will not run out of it, or interconnection to the main grid. That means, you keep multiple connection with your main grid, that one connection will get disrupted, at least you will get supply from other substation. Okay? That will be other than, it is a kind of transfer bus characteristics. That means, let us say this is your customers are connected like this, okay, but still here also you have a normally open switch. This is called a transfer bus, and this is called a main bus. So, what is happening when you want to supply the load, let us say this main bus goes out of order, at least you can give supply from the same generator by switching it on, and you can give the supply to your customers. Okay? For infrastructure resiliency involvement, you can do resilient transportation system for fuel and the equipment. Okay? That is your planning. You will keep your transport good, that in a very short time interval the fuel will reach to the thermal power or the nuclear power station. Then transmission system. You take corrective and preventive operational actions. That means, if something happens, you will take corrective actions that at least some portions of the load will be restored very quickly. and do the energy management strategies. That means you take the supply from any other resources. That means let us say something happened, you got disconnected from your main grid, turn on your diesel generator. Normally that is not on, but you can turn on and give supply to your customers. Okay. Other than that, for infrastructural, you install energy storage systems that will store the power for the backup supply and make resilient transmission technologies. That will make your transmission towers and the transmission lines very strong. For distribution system also, take the smart operational control and load balancing strategies. That means you make your system load balancing smart enough and take the operation control to your all your DERs inverters or your voltage regulators or all the resources, grid edge devices present, or say, let us say demand side management. This kind of strategies you adopt, that if something happens you can choose that which loads are critical and which loads are flexible. So you can segregate that with your backup supply from your distribution network, which part of the load has to be satisfied. So that analysis you can do from your smart operational control and load balancing strategies. Similar to the transmission network, for strengthening the grid, you can install distributed energy storage system and integration of resilient technology. That means make your construction of the poles or the lines in the distribution network or make your substations very strong. Okay. Then at the consumer level, use of flexible loads. That means if something happens, then you do not use your flexible loads. Let us say you get a very limited power. Already network operator told that we cannot supply you this much of power, and you are cutting it down and you have to consume less power, or we are giving backup supply from the diesel generator and we expect the diesel should be used optimally. If that is the case, so at that time you have to miserably or you have to wisely use the power. So at that time you will turn off your flexible load and just operate with your critical loads, okay, and employ demand side management. And for the infrastructure improvement, you can install own rooftop solar panel or let us say small micro turbines, micro wind turbines for as a DER supply, that at least you have a backup supply for yourself at least. And then thermal and local energy storage systems as well. Now, few terms we use in our power system which are more relevant to the resiliency, but they are not, they are related to the resiliency, but they are not resiliency. There is some relation between those terms and the resiliency. So, we will see what are those terms and how they are related with the resiliency. Okay. First, we will see accessibility. So, what is accessibility? Accessibility refers to the ability to gain access to infrastructural components and operational services, that you have access to something. Okay. In contrast with that, your resiliency focuses on the reaction of an event affected component. That means something happened and then your component has been affected. And accessibility means you have access, you have always availability of that component. So, they are related with each other with the response time and the recovery time. So, that means if something happens to your system or a component and it falls or it breaks down, then again it comes up to the restoration level and it is operating, that is called the resiliency. So, how first they are responding, how first they are recovering and then making them operational to the service, that is called the accessibility. That means after that you can access that service. Okay. The second term is the durability. So, what is durability? Refers to the capability of normal operation without demanding maintenance or repair over a period. That means that is very strong enough. You need not to maintain it, but still it will stand tall. It will operate without having any performance degradation. In contrast with the resiliency refers to the ability to withstand a disruptive event without collapsing over a period. And how they are related? They are related with the strength and the lifetime. So, if a system is durable, it is a very strength and its lifetime is very high, then it can also provide you enhanced resiliency services. Okay. Next, the second or third term I could say, that is the flexibility. What is flexibility? Refers to its ability to achieve stable operation after a disruptive event, even if it does not return to the original pre-event state. That means something happened, okay, but after some time it recovers and then it will go to a stable operation. Okay. That operation maybe not does not return to its original pre-event state. Okay. Means like previously it was generating 10 kilowatt and after some fault or something you recovered that fault and now it is generating, let us say, 8 kilowatt. It is in service but in a reduced manner. So, if that is there, then we call that system to be flexible. In contrast with that, what is resiliency? It refers to the system capacity to recover and return to the pre-event operating condition or a state closely resembling it. That means resiliency says no, you not only has to be stable, you has to be at that level what you was before the event. That means you have to restore the complete service. That means you have to go back to your 10 kilowatt. If that is possible, then only you will say that my system is resilient and as well as the flexibility, both are then same. So, how they are related? They are related with maintaining operation condition. That means you will maintain the operation condition of the equipment, then after the fault or after any disruption, if it recovers, it will go to its pre-event state. Then the fourth component, that is the robustness. It involves physically reinforcing energy infrastructure to reduce its vulnerability to disastrous events. That will reduce the vulnerability, that will make it strong. It will not become vulnerable. If it something is not vulnerable or doesn't, you can say, shake at the time of any disruption, then you can say he is very robust. Okay, that system is very robust. Compared to that, your resiliency focuses on the ability of energy services to recover from such events, accounting for both internal and external factors that impact the performance. Okay, and they are related with the strength and the maintenance. So, if you keep on strengthening or maintain your facilities in the network, then you can get a good resiliency and also your system will become robust together. Okay. Then the fifth term, that is the reliability, which is mostly, you can say, people use interchangeably, that resiliency as reliability and reliability as resiliency, but both the terms are not same. Reliability refers to the system response against high probability and low impact events. Reliability will check when the impact is low, but the probability of occurrence of that event is very high. Like let us say it is a fault, let us say single line to ground fault, that is very common in our system, but hurricane in our system, that is not very common, it happens once in a year. Okay. So, in contrast with that, resiliency says refers to the low probability but high impact events, which occurs very rarely, but when it occurs, it breaks down the entire system. Okay. So, reliable system may not be resilient. That means, if you can sustain a low impact high probability event, that does not mean that you will be good under high impact low probability event. Okay. So, that is only related when your failure impact and frequency is low. So, if the failure impact and occurrence frequency occurrence of that event is low, at that time you can say that a system is both reliable and resilience. Then the sixth term, that is the stability. What is stability? Ability of a power system to maintain or return to a steady operating condition after a small disturbance. That means a small disturbance is there, but it can still operate properly. Small disturbance, we know stability very well, but the resiliency of a power system to withstand, adapt to and recover from major disruptive events while maintaining critical functions. That means it has a big disruption, it has a small disruption. If your disruption is small, but still you can withstand that, we can say it is a stable system. When your disruption is very big, still you can withstand, then we can say the system is resilient system. So, both are related with the point that is called equilibrium point. After every event, all the system wants to go to an equilibrium event. If that achieves the equilibrium event, then we are saying that your system is stable and as well as resilient for a high disturbance event. Then survivability. What is survivability? Ability of a power system to maintain essential electric supply during and after disruptions using DERs to support critical loads even without the full service restoration. That means you do not have the full service restoration, but with some backup supply you are able to maintain the electrical connections or electric supply to your critical customers. So, resiliency is power system to survive, absorb and recover from disruptive events, with survivability being a fundamental component of resiliency. That means, survivability is a subset of resiliency, okay? And it will ensure the efficient operation. Okay. Now, the last term, that is the vulnerability. So, what is vulnerability? The degree to which a power system is susceptible to damage from disruptive events, that something happens and it will fall down. So, we call it a vulnerable system. But the resilience is completely opposite of that, that ability to absorb, adapt and recover from those disruption that you will recover. So, it depends upon damage intensity. If your damage intensity is very high, then you will become vulnerable and also your resiliency level is low. But if your damage intensity is low, then sometime you may be vulnerable, but sometime you may be good resilient as well. Okay? So, if you are resilient, then you are not vulnerable, or if you are vulnerable, then you are not resilient. So, this is a competitive system analysis of that. You can say that resiliency is the recovery and continuity of the system, and we do it by grid automation, DR integration, microgrids, fault isolation and service restoration. That means, you have a microgrid level, small local level, that will give you a backup supply for at the time of disruption. What is accessibility? Resource reach and response time. Relation with the resiliency is that enables faster recovery, improving resiliency. You have remote monitoring and control, mobile crews, inventory of spare parts and communication system. For durability, it is a long term endurance of the system, reduces failure probability, aiding system robustness, making the system more robust if it is a durable. Use of weather resistant materials, underground cable, pole reinforcement and maintenance schedule, that you can do for your power distribution system to make the system durable and as well as resilience. Flexibility is adaptability, supports continuity of service during disruption. DERs you can install, demand response, load reconfiguration, dynamic rerouting of the power. Those are the process to get the flexibility for a system. Robustness, it is withstanding the impact. Reduce system susceptibility, enhancing survivability. Okay. So, you make the system harden with the substation, your poles, your lines, your physical barriers and elevate the equipment in flood zone. Reliability, consistency and performance. You will make the system run for a consistent manner. So, minimize the routine outages and complementing the resiliency. Redundant paths you will create, that is with the normal open switches. Advanced protection system that can easily detect and sense the faults, predictive maintenance, SCADA system and etc. Stability, operational balance ensures smooth operation performance during recovery. Voltage regulation, reactive power compensation, real time system balancing and capacitor banks are good for maintaining the stability. That is the reactive power supply, active power supply or voltage support you can give to maintain the voltage and the rotor angle stability. Survivability you can get from minimum service level, subset of resiliency ensure basic functionality, and you can get it by backup generators, priority loads, microgrids, local energy storage for critical infrastructure like hospital. At last, vulnerability, it is more exposure to the risk, inversely proportional to the resiliency, just what I told. If your system is resilient, then it is not vulnerable, and if it is vulnerable, then it is not resilient. So, to improve your vulnerability, you can do the risk assessment, hazard mapping, asset critically analysis and infrastructure upgrade in high risk areas. So, how you will do the resiliency evaluation framework? First stage, stage 1 is identification and classification of the disastrous event. That means, this stage involves analyzing the characteristics of the potential disaster event, such as their magnitude, likelihood and spatio-temporal distribution, using both deterministic and probabilistic model. Okay? That means, first you have to identify that which kind of disasters you are going to experience in the network. If you do not know that, then how will you do the study? So, the first stage is that you will study the disastrous event, and from where? First, your deterministic model rely on historical data. That means, you have historical data of your hurricanes, your floods, earthquake, this data you have. So, from that weather records you can take that when it is happening and what is the weather condition for it, and if it happens then what the preventive measures we are taking, or the probabilistic models to simulate possible future events using statistical models of earthquake or floods. You can take probability distribution functions of them, then generate the scenarios like your probabilistic OPS studies. So, what you will get? Disaster classification based on potential threat. So, you will get different disasters that will affect your distribution network. Second, you feed that classification disaster information to your stage 2 for analyzing the vulnerability analysis of power system components. So, you have got the disaster, now you have to check how much your system can sustain that disaster. So, that is the vulnerability checking. This phase focuses on assessing how different components of the power system may be affected by the disaster. Components are divided into macro components like your power plant, substation, transmission lines, or micro components like breakers and the switches. Fragility curve are used to model the probability of failure of each component type based on the event intensity. Okay, that is the fragility curve normally will design that will say the probability of the failure of an specific component or equipment depending upon the measure or intensity measure of the disaster event. Okay. Components are assigned to various damage states according to their fragility curves and specific failure threshold. And as an output of stage 2, what you will get? Identify weak links or fragile components in the network. So, first you identified the disaster, then you simulated that your power system components with that disaster and see if your system is vulnerable or not. If it is vulnerable, which poles or which lines or which substation is more vulnerable if they are exposed to that such events. So, get the identify weak links and then feed that to the stage 3, that is the system response to disaster. This step evaluates how the distribution system reacts to that disruption. That means, if you already know the fragility, so you know these components will fall down or breaks down when this kind of natural hazards or disruption occurs in the nature. Okay. It uses simulation models to analyze cascading failures and blackout scenarios. That means, if one pole falls down, whether the neighboring poles also falls down or not. So, this is called cascading effect. So, we have to check with the simulation models how much cascading failures you will experience. Simulate the critical infrastructure reactions under stress. These models help to predict how disruptions spread and identify failure points in protection or control systems. Okay. Solve the ACOPF model for de-dispatch command generation. Then after that, everything happens. So, you have to now see that how much you can, what is the, after falling down your components of due to the disaster, now how your system will behave, whether you can solve your power flow or optimal power flow. If it is possible, so that means you have to revise your generating setting or your other dispatch setting. So, that you have to determine from this system response and disaster stage. So, what you will get as an output, you will get to the response to the disaster. Then that response you will use for the recovery and restoration of the power system. So, this stage assesses the restoration timeline and capability after a disruption has occurred. So, key factors are the cause of the disaster, availability of the human resources, and accessibility of affected components or regions. So, that with that ACOPF solving, you got that some portion of the system is becoming dark. So, how many persons are affected? So, what is the disaster is causing or resulting in your network? So, those things you will note it down, and depending upon that you will take restoration time after disaster. That means, how much time you need to again connect those customers with your system. So, this is a typical resiliency curve generally we follow to model the resiliency operation. This is generally for the operational resilience. Okay. So, this is your normal operation or your pre-event operation. So, something happened after at the time of TE. So, what will happen? First, the system will start falling down. It will not that suddenly everything will fall down, one by one it will happen. So, first the system will become alert with the inadequate security margins. If that happens, that means your security is not adequate, then the emergency situation will occur. And after that, the cascading outage will start. And then the performance, you can notice the performance of the system or the resilience level of the system is falling down. And when this is the event state or event time, when during the event what is happening. So, at the starting of the event, your resiliency will go down, and after certain time it will become saturated. That means, let us say all the poles have fallen down. So, nothing more can happen to you. So, this is your extreme event condition. So, now at TPR your event has ended. That means, your hurricane has passed from you, okay, passed out from you. So, after that your restoration you will start. That means, all the rescue team will reach there, they will start building the facilities, or they will see whether there is a backup supply or not. So, then the restorative action will start, and that will bring the system to the normal level. Okay. So, this is the operational resilience. So, depending upon that, we are using this trapezoid function to see the resiliency performance. What it says, the disaster events, you have a pre-disaster condition, then damage will propagate and your resiliency or performance level will decrease. Then at the post disturbance, you will have minimum, and then you will start the recovery. And at the post recovery, it is possible that you will not reach to your exactly pre-event state. So, this is the gap between your pre-event and your post-event restoration. So, this is your initial level and this is your final level, okay, and this is your disrupted level. So, targeted performance is 100%, but the actual performance level is lesser than 100%. So, this is the 0 to T1 is your pre-event, T1 to T2 is the damage propagation or disaster propagation, T2 to T3 it is the post disaster period when disaster went out, but you have not started the recovery stage, T3 to T4 when you start the recovery, and T4 to T when you complete the recovery. So, depending upon that we define the resiliency index. Okay. So, what is the resiliency index for the critical infrastructure encountering a severe disaster within a certain interval 0 to T. So, it says how much you recovered by how much you lost. That means, if this is a P time, that means if the system operates like this, then this should be your response. But now currently because of this level you got this response. This should be, this is your ideal and this is your actual. So, this is the ratio between the actual and the ideal, and if it is close to 1, that means you are operating more ideally. That means you have restored all of your connection or all of your components to the pre-event state. Another resiliency index that normally considering only the damage propagation and the recovery time states. That means it is called PAT4, that means that portion minus PAT2, that means that portion, that means where you T2 or T3. So, that means post disaster how much was there and after recovery where were you, and that is the difference between that and actually T1 minus T2. If this is your T1, this means T2. So, how much you have lost and how much you have gained. If that is also close to 1, then that means how much you have lost, you have gained that much. So, that is good, then you can say that your system resilience is very high. So, other indices also we use, that is the how quickly the damage is restored, how quickly the system is damaged by the disastrous event, that is given by the time, like how much you have lost in how many durations, how low the system is degraded by a disastrous event, that is difference between these two gap, then how long the system remains degraded, that means the time difference between T3 and T2, that is the post disturbance, that means your event ended and but you have not started your recovery. So, that time gap. Then how quickly the system is recovered after disastrous event, that is between your T4 T3, that means the rate of recovery, that how quickly you have recovered. If this time is very small, then that means your recovery state is very high. So, this is the resilience triangle. Other than the trapezoid also we use the resilience triangle. That means either you can do the slow recovery or you can do the fast recovery and you can reach to the your pre-disaster area. So, other than trapezoid, you can also represent your resiliency with the help of a triangle. So, the resilience triangle depicts the performance deterioration of a grid asset over time for an extreme event. Okay? And the models you need for the resiliency study. So, we need few models, right, to do the resiliency study. We know the curve, we know what is happening in the system, but if you cannot model them in a mathematical manner, then how will you simulate them? So, for that you need the climate model, which will have the historical data, environmental stress, this thing you will simulate with the help of historical weather and the synthetic data. So, that is the purpose of that, that link the climate condition with the component failure, and this model you will feed to your next model, that is the component level model. And then your weather model you will integrate with the few components, their mechanical strength, and see whether your individual components can withstand that weather impact or not. Okay? And then that will give you the vulnerability analysis of your each and every component, and there you can derive the fragility curve for each and every component. After you got your component model, feed that component model to the system. So, now your system will say which links are fragile or which components are more weaker. So, if something is happening, so this component will fail down very easily. So, that aggregated component data, time series weather simulation data and spatio-temporal data, you will feed to the system with the overall climate model and your component level model, and you will use them for the evaluation of the wide performance under various weather driven scenarios. So, this is the distribution system resiliency enhancement you can do. With the planning stage you can plan resiliently, and the operational stage you can do preventative response, emergency response or service restoration. So, we have discussed these things. In the preventive response you can do grid hardening of the distribution system to minimize the effect of the severe conditions. For making them more survival, to enhance their survivability, services carried out limited activities without relying on the main grid. That means, you have backup supply, and then do the recovery by complete restoration of the electric supply to all the affected customers with the help of backup supply possible. So, these are the planning things. You can do the vegetation management for the good planning of your infrastructure to maintain your resiliency. That means, you cut your trees properly, the branches at least, you cut the branches that will not fall down on your power line, harden the lines with a good material and also the poles, upgrade the component time to time, do the maintenance and give the backup facility. So, that is at the planning level, and the operation level, if something happens, so at that time you cannot plan for the next step. So, at that time you have to act very fast. So, at that time you can have microgrid formation, little bit of cluster of DERs you have. So, you can take power from them to give supply to your customers. You can do network reconfiguration. If something happened and some lines goes out of order, so you can reroute your power supply to your dark customers from a longer path. Okay? And you have mobile emergency energy storage. You can have mobile energy storage and you can just send them to your customers, that it can be, your supply can be restored from those mobile energy storages very easily. So, take those restoration methods, document them, that whenever next time something happens you can act very fast. Okay. With this I will end today's lecture and we will continue with our resiliency study in the next class. Thank you.